Yes, there is a cross on start video. Maybe now it allows.
You are visible now also. Yeah.
Am I visible now?
Yes, yes.
Okay, nice.
Now, please try to share once, and then we can.
Is it
Yes.
coming?
Yes, yes.
So now video is also on or video is on?
Video is off now. Okay.
So I don't know how to manage this because it is turning off. I'm using iPad. So should I join from two devices or what?
Yeah, you can do. You can do. No issue.
But well, then I will be facing in some other direction.
Yeah, you have time.
Let me try to adjust it. Stop my video. Now the screen should be coming, right?
I can see your file, but
My video must have gone, right, by now?
yes.
Yeah, it's visible.
Video is also visible?
No, video is not.
Yeah, your video was visible, but not now.
Yeah, when he is
So
changing.
that's what I'm joining from one more device.
Hi, this is Atul.
Oh,
Hi, sir.
hi.
Hi, I'm unable to start my video. It says the host has disabled.
Okay.
Yeah, exactly. I am facing the same problem.
Okay. We have
Okay.
So who is there? The IT people. The Samuel. Could you fix the problem? Mr. Samuel, could you fix the problem? So people are not able to see their video.
And other thing that I cannot join from two device. It says that you have already joined.
Okay.
So is it okay without video?
It's
maybe
okay.
in the beginning.
So without video is okay.
No, start.
But I don't know why they are facing this kind of problem. Yeah. So, sir, you are visible now.
Oh, I'm visible? Okay, good.
Is my video visible now?
Yes.
And let me know now.
No.
Yeah, so this is the problem. When I switch to the iPad, meaning my slides, then video goes off automatically.
Okay. Samuel, is it possible to fix the problem?
Maybe it is from my device or.
No, maybe our university Zoom settings, some problem is there. Who is there now? Samuel, I think.
We can see Atul sir's videos, so I think it should not be the issue. Maybe it is the iPad's issue.
Yeah, it may be. That's what I was asking.
Yeah, now we can see. Now we can see your video.
Yeah, because I'm on the Zoom page, not on my slide page.
Yeah.
So if I go to my slides,
yes,
it might have gone out.
Yeah, that's okay.
Okay, still it's okay. No issue.
Okay, up to you. But this is very, it's just sort of weird. You don't see me, you only hear me.
Okay.
Hi, Shiprakash. This is Suratno.
Oh, hi, Suratno. How are you?
Yeah, fine. After a long time, I'm seeing you, but virtually.
Yeah, correct. I think last time I saw you in IMSC, right?
Yeah, that too, I think long time.
Yeah, long back. Several years back.
Several years.
I think it was maybe 18 or 19.
Yeah.
Maybe 19. 2019. No.
Yeah, actually, I left in 2016 just for a year. Again, in 17, I came back to Chennai. So, yeah, maybe 17.
So you are at ISRM, right?
Yeah.
Okay.
You are in Delhi?
Right.
Yeah. One of our colleague in computer science recently joined, Nikhil Walaji. Did you happen to?
I know the name, but I don't know him personally.
I see.
And another person from IMSC you might know, Asutosh Rai.
Yeah. They were junior. Yes.
So
He
he is
also tried.
in our department only.
Oh, I see. He did in computer science, I think.
Correct, correct.
So we can start now.
Yeah.
Yeah.
2 o'clock.
Okay. Should we start?
Yes, sir. Yes.
Okay. Good afternoon, everyone. Welcome to the afternoon session of the last day of the conference today. So our first speaker in this session is Professor Shiv Prakash Patel from IIT Delhi, and he'll be talking on restriction of representations from GL2F to SL2F. Over to you, Professor Patel.
Yeah, thank you so much for kind introduction. And before maybe I start talking about the research work here, let me thank the organizers, especially Sajjad and Manish, who gave me an opportunity to speak here. So today I will be talking about restriction of representations. So here the groups which I will take, I will be describing them. I have denoted them by GL2 tilde to SL2 tilde. Unlike linear groups, these are not linear groups, meaning in some sense, which I will be describing in few minutes. So let me just tell you very shortly that what is the restriction problem in representation. So restriction problem, I mean, the question is, it's very simple-minded. So what we have, we have a group. Here I am writing G and we have a subgroup. And we take irreducible representation of G and another irreducible representation of X. I am calling them pi and sigma. And of course, representation of G, it can also be thought of as a representation of H, which we call, you restrict the representation pi from G to H. So sometimes you write pi restricted to H, but here I am not writing. I am just taking the usual notation. So what is the multiplicity? Multiplicity is defined to be the dimension of Hom H pi to sigma. So pi is a representation of G, which is also a representation of H, and sigma I'm taking to be a representation of H. So I take the H homomorphism from pi to sigma. And this is a vector space, and the dimension of this vector space, what we call the multiplicity of sigma inside pi. And here, of course, the main question which we will be dealing today is for certain groups and for certain subgroups, we would like to know what is the multiplicity, what is this number. And if you are lucky, if multiplicity is 1, in that case, we call that sigma appears in pi with multiplicity 1. And our main focus is going to have those groups and subgroups and those representations for which multiplicity is finite. Of course, and nobody stops you, stops it to be finite. It may be infinite in some cases, but what we will be dealing is they will be having finite multiplicity. And of course, if you have multiplicity 1, those are more important cases. So the restriction problem is very simple-minded. So you have a representation of a group and you want to restrict it to certain subgroups. And of course, restriction to the subgroup may not be irreducible. So it breaks up into irreducible component in some language. For example, in for finite groups, that is always the case. Meaning if you have a representation restricted to any subgroup, it is always direct sum of representation if your group is finite. But if it is not finite, that may not happen. So I define it to be this dimension. Okay, so I will be talking about groups which involve the definition will involve local field. So I will just give you a quick review of what is a local field. This is just a reminder. So what is a local field? By definition, a local field is a field, of course, which has a topology, and topology is locally compact. Of course, locally compact topological field meaning addition map and product map and the inverse map on the invertible elements, all those maps are continuous. And here we demand that topology to be locally compact topology. Of course, I'm excluding the case to be for those with the discrete topology. Technically, those are also locally compact, but by definition, I'm taking to be non-discrete. And what are the examples of local fields? Real numbers, complex numbers, and field of periodic numbers. And you can take the function field over a finite field. This is also a local field. And of course, you can take their finite extensions of any of them. That is also going to be a local. So, if I mean, what I'm going to say is going to be true for any non-Archimedean local field, meaning fields except R and C. R and C are what are called Archimedean fields. Other local fields are called non-Archimedean local fields. So, for maybe today it is for general local field, but maybe for to keep something in mind, we can think of just QP. So what is QP? You know, QP has a compact subring, which we usually write by the letter ZP, and this ring has plenty of ideals which are generated by the elements p power n. So, for example, ideal generated by P is going to be a maximal ideal of this ring ZP. So it has a lot of open, closed, and compact subgroups. So ZP, so for every n p power n ZP, this is an ideal which is a open, closed, and compact in ZP. Of course, therefore in QP also. So you see this group QP as a topological group. It has around 0. It has lot of open and compact subgroups. So you can notice that in real number, this does not happen. We don't have open and compact subgroups of real numbers. But in the case of non-Archimedean local field, this happens. And in fact, if you recall the topology, the subgroup p power n ZP, these give a basis for the topology near C. And similar thing you can see for the multiplicative group of QP star. So QP star meaning QP minus 0. So this is a group, and this group has this subgroup ZP star. This is a compact subgroup, and it has lot of subgroups which are open and compact. Lot of meaning there are infinitely many, of course. 1 plus p power n ZP time. For any n, you will get lot of subgroups. So in this case, these subgroups, they will give a basis for the topology near one. Okay, this is reminder for the local field, non-Archimedean local fields. So if what I want to emphasize here is that in these cases, whether you take additive group or the multiplicative group, around the identity element of that group, there are plenty of open and compact subgroups. Okay. So here on this page, what I will be talking, it is going to be for general linear algebraic group, but we will be giving examples for GL2 because you know our talk is going to be mostly either about GL2 or something very related. So for any linear algebraic group, you look at f points of the linear algebraic group. And since F is locally compact topological field, the F points of that group that also becomes a locally compact topological group. And in fact, it has a basis for the topology near the identity element, like in the periodic field. whether additive structure or the multiplicative structure, both kind of groups, they have compact open subgroups near identity. And that was forming a basis for the topology. So same thing happens for f points of any linear algebraic group. So as an example, if your GL2F, F is a non-Archimedean local field, but if for simplicity, maybe we can take it to be QP. Okay, so then you look at OF. OF is the maximal compact ring of that field F. For example, if it F was QP, then OF is going to be ZP. If you look at ZP point of GL2, then you get these kinds of subgroups of this compact group. And these are what form a basis for the topology near the identity element of the group GL2F. So the important part, maybe I will say once more that over the non-Archimedean local field, there is a whole supply of open and compact subgroups near identity element.
So what is this notation M2OF? Can you?
Yeah, M2 is the set of all matrices with entries in OF.
Okay.
For example, M2ZP kind of. Yeah. So if you take one identity plus some matrix with ZP entry, that is going to be invertible. Not maybe ZP, but P times ZP. I'm taking here n greater than or equal to. So you take this pi is nothing but P in case of Q.
Okay, 1 plus.
So I
that.
again, yeah, please.
Okay, you are saying 1 plus that will be invertible.
Yeah, it's like 1 plus P is invertible.
Yes.
In QP, in ZP. Yeah. And I again remind you that such a thing you don't have for GL2 if you consider real number, meaning the Archimedean. All right. So let me, given on what we have, meaning lot of open compact subgroups, let me tell you what are admissible representations for a periodic group. So here G is again something like GL2 QP. You can think of this. So this is what we call periodic group. So we have this group and a vector space or complex number. So I will always, whenever I say a vector space, it is always a complex number. So by definition, a representation is going to be a homomorphism from G to GL of. And such a representation, of course, this can also be thought of as G cross V to V, meaning there is an action of G on the vector space V. Only thing is that every element of the group acts in a linear way. And such a representation you call smooth when stabilizer of any vector, stabilizer is going to be a subgroup, and this subgroup is open. If stabilizer of every vector is open, you call the representation to be smooth. And of course, here you see, remember, we have a lot of open and compact subgroups. So therefore, such a thing makes sense. For example, real number, we cannot make such definitions. Because let's say for real number, if you take open subgroup, it will have to be all of real number. And you call a representation to be admissible if for every open compact subgroup, or maybe just for open subgroups, that is also enough. For any open subgroup, Vk is going to be Vk meaning fixed points under the action of K. This subspace should be finite dimensional. Then you call it admissible. So, I mean, these technicalities are not going to come what I am going to describe, but since I will be talking about only these kind of representations, so I thought I should give a definition. And in case of GL2, what are all irreducible admissible representation? They fall into, let's say, in these 4 types. I have written just names. So some of them are like you take the determinant and then composed with a character of F star. So those are all one-dimensional representation. And then one has a induction from the upper triangular matrices. Those are what are called principal series representations. And many times they can be irreducible. So the irreducible principal series representations, they fall into one type. And then we have Steinberg representation, meaning when we do this induction from the upper triangular matrices, when it is reducible, it breaks up into two components, and one component is one dimensional like this, and the other component is going to be some infinite dimensional representation. We call that Steinberg by definition. And all other representations are what are called super custom representations. And these two kinds combined, they are called discrete series representation. In the case of GL2, of course, I'm not defining here what is a discrete series. In sense, they have the matrix coefficients of discrete series representations. They have modulo center, the support is compact. But anyway, these technicalities are not going to come. So, I mean, in whatever I described, only these words will come. Okay, so whatever I said so far was for linear groups. In fact, I just told you about GL2. And now let me tell you what is a covering group. If you have a group G and an abelian group A, this is an abelian group. And I call another group G tilde to be a central extension of G by A. If you have a this G tilde, A sits inside G tilde, and G tilde projects onto G. And this is a short exact sequence, meaning kernel of this projection map is sorry. This is a short exact sequence. The kernel of the projection is nothing but isomorphic to A, meaning image of it. And you call it central extension when the image of A inside G tilde is in the center of this G tilde. So that's what I wrote here. The image of A is part of the center of the group G tilde, meaning this covering group, what we want to call. And from, if you want to describe how many central extensions are there for given G and A, then in algebra we know that that isomorphism classes of central extensions they are parameterized by H2GA, meaning this is the second cohomology. And so explicit cocycle for this cohomology corresponding to whatever extension I am going to take, I will describe part of it. And in fact, what I am going to discuss is that just two-fold cover of the group GL2, meaning you take this G to be GL2 and the abelian group to be this group of order 2. So this is what I will be calling two-fold extension of GL2, meaning extension of GL2 by the group of order 2. And this is just a warning that unlike GL2F, this is a F point of a linear algebraic group. But these covering groups, which I am going to consider, these are not F point of any algebraic group. So these are somehow this family of groups is away from those which you get from algebraic groups, but they are very much related. There is plenty of similarity between them. And as I described here, that one isomorphism class is going to correspond to let's say two cocycle, one element of H2GA. And in this case, the cover which this two-fold cover, which I want to consider, it corresponds to, of course, the cocycle with values in ±1. And you can write down an explicit cocycle. And in fact, if you take, let's say, GLN or something, then writing down a cocycle is quite complicated. But in this case of GL2, you can write down explicit cocycles. You call them Kubota cocycle. Of course, the cocycles are not unique because they can always be multiplied by a co-boundary. So, but there is a very special choice which makes a lot of computation easier. I will define. I will describe on part of the circuit. Okay, this is a generality about how covering groups arise. And they arise from this H2GA. And in case of which group I am going to consider this GL2 tilde, as I said, I have not defined it. In fact, I will not explicitly define in that form, but I will tell you how you get subgroup. So, I mean, this can be easily seen that GL2 is a semi-direct product of SL2 with F star. How do you see this F star as a subgroup of GL2F? You can see it in the first diagonal entry. So A going to diagonal matrix A1. You can of course take the other one, meaning 1, 0, 0, 3. Still, this will give you the semi-direct product. So GL2, it is it can be seen as a semi-direct product, and for this group SL2, one knows that there is a one non-trivial two-fold cover. Non-trivial two-fold cover of SL2. It exists. I mean, this construction was given by Weil in his 1964 paper. So that I take for granted, and which I will be calling metaplectic cover, and I will denote it by SL2 theta. And so this group, this subgroup of GL2, it has a unique two-fold non-trivial cover. And if this semi-direct product, for example, F star is acting on SL2F by conjugation. If I can lift this action of F star on SL2 to this new subgroup SL2 tilde, then I can define such a semi-direct product. And that is what I will call two-fold cover of GL2. In fact, this happens. This action of F star on SL2F, it extends to an action on SL2F. So this has to be justified. Okay, this happens. I'm telling you this happens, and then this definition makes sense. I just take the semi-direct product and I'm calling it GL2 tilde, which of course is a two-fold cover of GL2. Okay, so let me tell you how the if you want to, let's say, understand cocycle, these commutators give you a fair enough idea how the cocycle looks like. For example, let's say sigma from G cross G to group of order 2 plus minus 1. If the cocycle I want to define, so it looks something like this. Let's say A, B diagonal, another matrix C, D diagonal. This cocycle comes out to be A, comma, D. This is the Hilbert symbol over H. So this is how cocycle on diagonal circuit looks like. But if you want to describe on the whole of GL2, then it's more complicated. I mean, I have a formula which I can show, but it is not so important here. But what is important to note here is this commutator. If you take two diagonal matrices, let's say AB and CD, and you can take their, you remember this GL2 tilde of F to GL2 of F, I have this projection map. If I have a matrix here, I can take its inverse image. Of course, there are two inverse images, so you take any of them. Because the other element, it will just differ by that plus minus 1, which is anyway central element. So that will not play any role when you talk about the commutator. So you take any left A tilde, B tilde, these are elements of GL2 tilde. Of course, if you take the commutator inside GL2 of A and B, it is 1. because these are this is a commutative subgroup. The diagonals they form a commutative subgroup, but here it is given by this formula. So here, whenever I write A comma B, this is Hilbert syndrome. Okay, so this may be +1 or -1. It depends. And of course, it happens that it is many times -1. So therefore, this group is not commutative. So, let me. So here, what I have proved is that the inverse image of the diagonals is a non-abelian subgroup of GFP. And let me fix up certain notations. So for any subgroup X, I will be writing X tilde for the inverse image, the whole inverse image set. And a center of GL2, I know that this is a scalar matrices which can be identified with F star. And but the center of your the two-fold cover of GL2, it is not the inverse image of this. Okay, so this is not equal to the inverse image of F star. What happens? The center is not the inverse image of F star, but the square elements in the center. You take the square elements and then take their inverse image. This is the center of GL2 theta. And as I mentioned earlier, if you take the diagonal torus, I'm writing that to be T, then T tilde, the inverse image is not abelian because we just saw that the commutator is sometimes not equal to 1. Okay. And if you look at the upper triangular unipotent matrix, that subgroup, which I'm writing N, then the inverse image comes out to be isomorphic to direct product. So this is no longer a genuine cover, meaning it's a trivial cover. It splits over this subgroup. So N can be seen as a subgroup of N tilde, therefore a subgroup of GL2 tilde. Okay, so since N splits, the similar notion as I was saying, the parabolic inductions, which are in case of GL2, these are inductions from upper triangular matrices. That perfectly makes sense here. And parabolic induction and Jacques functor, these things which are there for linear groups, they also can be defined in case of covering groups. And since these are covering groups, I don't want to consider the representations of GL2 which come from GL2. Meaning, you look at, I am having such a, I mean, there is this subgroup of order 2 of GL2 tilde, which is central. So any representation of GL2, it can be brought back to a representation of GL2. And those representations we don't want to discuss because those are nothing but representations of GL2. So we only want to discuss those representations which are non-trivial on this group of order 2. And those are what we call genuine representations, which are non-trivial on plus minus 1. Meaning it will have to be plus 1 on 1 and minus 1 on the minus 1. And in this case also, representations you can call some of them to be supercuspidals, meaning those which do not come from the parabolic induction, I mean subquotient of principal series. So representations will either be a subquotient of a principal series or they are called supercuspidals. Okay, so let me tell you something more about GL2 tilde and what I'm going to describe now. So far, I was giving you some background how covering group looks like, but now I want to talk some more properties of this GL2 tilde, which are going to be relevant. So SL2 tilde, of course, SL2 tilde, whenever I say this is always a subgroup of GL2 tilde, the way we have described it. So when you talk about centralizer of SL2 tilde, it is Z tilde. Z was the center of GL2, meaning Z is the set of scalar matrices inside GL2. So centralizer of is this, then I define new group. I take the product of them. I am writing a symbol plus here. So GL2 plus. So these are, this is a subgroup of GL2. Okay, this subgroup plays an important role, what I am going to discuss. And you can notice that this subgroup, it has finite index. So GL2, and of course, this is normal. You can, well, this is normal subgroup, and you take the inverse image, that image normal. And the quotient is a finite group. The quotient, you can see it is isomorphic to F star mod to F star square. And this set is finite. So we have constructed a subgroup of finite index. And since Z tilde and SL2 tilde, they commute with each other, I take a representation of SL2 tilde and calling that tau. And I take a character mu of Z tilde. I want to combine them and combination I am calling mu into T. This I want to make a representation of GL2 plus, meaning the product. One character, because Z tilde is abelian, so mu is going to be a character, and SL2 tilde representation is any genuine irreducible representation. So of course, they cannot always be clubbed together because there is some intersection between Z tilde and SL2 tilde, and we call them to be compatible if they agree on the intersection. Okay, so you take mu and tau which are compatible, meaning they agree on the intersection. Then you can form mu tau, which is going to be a representation of GL2 F plus. And here the vector space is going to be the same vector space of tau, corresponding to tau. And since I mentioned that this is a finite group, and representatives of this quotient I can take to be of this form. And if I have a character of Z tilde, I can twist that character by A. Here, what do I mean by twisting? So mu A of Z tilde is by definition is mu. You take this matrix. Sorry. Let me write again. So mu A of Z tilde, it is going to be by definition mu of the matrix corresponding to A, which I am writing GA, Z tilde, GA inverse. This is the character which I am writing mu A. And when you compute how this conjugation, and then you get mu of Z tilde and Hilbert symbol of A comma Z. So Z tilde is going to be some element, Z tilde is going to be some element Z comma, let's say 1 or minus 1, plus minus 1. Okay. So, and since Hilbert symbol, whatever appears here, this Hilbert symbol is non-degenerate on F star modulo F star square, this property I'm using. Okay, this non-degeneracy of Hilbert symbol. This tells you that if A is not a square element of the field, then the twist is never equal to mu. It is always going to be different character. Okay. Then how do you construct representation of GL2 tilde from representations of SL2 tilde? Because I want to discuss restrictions from GL2 tilde to SL2 tilde. So there is some interplay going on between them. So I have summarized that in this lemma. So let me first explain the notation. So I have a character mu of Z tilde and a representation of SL2 tilde, mu and tau. And I assume them to be compatible, meaning they agree on the intersection. And then mu tau and the conjugate of mu tau, this representation, they are not isomorphic. Why they are not isomorphic? Because this representation is going to be mu A, tau A. And mu A is not going to be equal to mu. Because just I said that this follows from non-degeneracy of Hilbert symbol. Okay, so this is very important property that if you have representation of GL2 tilde plus, it was this subgroup. Remember, this is a representation of this GL2 tilde F plus. So any representation of GL2 tilde F plus and its a twist, they are never isomorphic. And what happens now, you can use Mackey theory that every genuine irreducible representation phi tilde of GL2 is given by induction from this finite index set. You can easily prove that the induction is going to be irreducible because all their twists are different, meaning non-isomorphic. So this induction is irreducible, follows from Mackey theory. And when you restrict it to GL2 F tilde, you get all conjugates of that representation mu tau. And there will be only finitely many of them because this F star modulo F star square is finite. And if you further restrict it to SL2 tilde, then of course mu will disappear because you are removing sort of Z tilde. So only you get tau. It is going to be direct sum of tau A, twists of tau, all possible twists here. Okay, so this is going to somehow help in answering the question which I want to understand. You see, what I'm trying to do here is that I have a representation of GL2 tilde, and I want to describe how this restriction to SL2 tilde it looks like. Meaning, I wanted to know how many times this tau comes up. So it may happen that tau may be equal to tau A. So that is how many times it is equal, that will give you the multiplicity. Okay. And to define, to come up to some answer, I will be using two more words, which I will, one of them is theta correspondence and other is Jacob-Langdon correspondence. So let me briefly describe. So remember, I just want to describe this restriction, meaning how many tau A is isomorphic to tau. That will give you multiplicity of tau. Okay, so let me very briefly tell you what is theta correspondence. So to define theta correspondence, one has to fix a character, additive character of the phi. And new notation is coming up here, D. D is a quaternion division algebra. Of course, there is only one quaternion division algebra here. Of course, center is going to be F. Then D star, the multiplicative group, you go modulo F star, the center of D star. I am writing that as PD star. Like, you know, you have GL2F, you go modulo center of it, you call that PGL2. Similarly, you go modulo the center of D star, you call it PD star. So what is theta correspondence? Theta correspondence is a bijective map from set of all, when I say just irreducible, here in the case of covering group, I also take them to be genuine representations. So set of all genuine, irreducible, admissible representations to the union of two sets. One of them is the set of all irreducible representations of PGL2, other is irreducible representation of PD star. And maybe just for information, PD star is a compact group. These are non-compact, but when you go modulo the center, this is a compact group. So irreducible representations of this group are always finite dimensional. But here, they are either one dimensional or infinite dimensional. So if you notice this bijection, then some of the representations of SL2 tilde, they will map into PGL2, and some representations will map into the representations of PD star. So sort of it, this set is being divided into two parts. Okay, so that is going to come until later. So if suppose I take two representations here, let's say phi 1 and phi 2. both of them may go to the same, let's say PGL2. Then we call that pi1 and pi2 are in the domain for PGL2. If they go into PD star, then we will say that pi1 and pi2, they belong to the domain for PD star. If they go to different ones, of course, they have different domains. That kind of language I will be using. And what is Jackie-Langland correspondence? I'm not going to give any details here. Jackie-Langland correspondence is a correspondence between irreducible representations of PGL2 to irreducible representations of PD star. So here I'm not saying that every irreducible representation will always correspond. Okay, for example, principal series do not correspond to any representation here. It's only discrete series representations. They have the correspondence here, but I'm being a little bit vague here. So just to have fixed an idea, what is going on, that representations here, they correspond to some representations of PD star. All right. So now we have this theta correspondence. Maybe sometimes I will not be writing theta, this notation psi. I may suppress it. So I have theta correspondence and Jackie-Langland correspondence. I'm going to combine it to get an involution on this set of all irreducible representations of SL2 tilde. So of course, SL2 tilde to theta correspondence, it will go to PGL2. Of course, here every representation will not correspond. Some representations will, of course, go to PD star. So I'm writing a different line for that. And they should not be seen as maps, okay, because on some of them it is not defined. And from PGL2 to Jackie-Langland, this is Jackie-Langland correspondence. So what happens? Let's see. You have sigma, some representation. Suppose it goes to PGL2, you follow this path. And suppose it has a Jackie-Langland correspondence, you go to PD star. Then you try to see if it was a free image of something. So that is what we will call sigma W. Okay. So sigma in other way. So sigma and sigma W, this is what I am calling Walsh-Forge involution. How to understand this? You take the representation, it will go to either PGL2 or PD star. Suppose it goes to PGL. And then you take Jackie-Langland correspondence, you go to PD star, and then you see which representation was of SL2 tilde was coming to that particular representation. This is what Walsh-Forge involution. So it is going to come what I want to describe. All right, so we get an involution. And this is a theorem of Walsh-Forge. What it tells us, how it tells us to identify. So maybe since I don't have much time, so let me just describe in some technical way the way it has been written here. So if I try to give the ideas here, then it will take some time. So fix this character because I want to write the theta correspondence. Although I will not be writing theta with psi all the time. Here I am writing this theta. So fix this character for theta correspondence, and for any fixed invertible elements, you define this character given by the Hilbert chain, and fix this tau of SL2 tilde, this reducible representation. Then you look at tau and the twist of tau. These two representations, they may or may not be in the domain of the theta correspondence for the same group, meaning you look at tau and tau e. Okay, both of them may be in the, let's say, domain for PGL2, or both of them might be in domain for PD star, or it may happen that one of them is in the domain of PGL2 and other is in the domain of PD star. So this theorem, it tells you precisely when both of them are in the domain of PGL2 or in the domain of PD star. Being in the same domain is equivalent to, yeah.
Yeah, is there any condition on chi, conductor condition or something like that?
No, here there is no
Any
condition.
quadratic character will work?
Yes, yes.
Okay.
So this equivalent condition, meaning for them being in the domain of the same group, meaning either of PGL2 or of PD star, the condition is this epsilon value. So this epsilon value you can think of. So theta tau is going to be, let's say, representation of PGL2. Then you can use local Lagrange correspondence, and epsilon value is nothing but the coming from the corresponding Delver representation. Okay, so if this epsilon value satisfy, so you have one representation of PGL2 here and other representation of PGL2 here. So one is the twist by this quadratic character, and if epsilon values differ by the quadratic character at -1, then they will be in the domain of same group, meaning either both of them will go to PGL2 or both of them will go to PD star. And if that happens, what is this theta of the twisted representation? So theta of the twisted representation is going to be the earlier representation twisted by the quadratic character phi. And if both of them, tau and tau a, if both of them go to different ones, meaning one of them go to PGL2, other goes to PD star, then here you get minus sign. So if you get a minus sign here, and I'm just assuming that, let's say tau is going to be in PGL2, then the twist will go to, of course, PD star. And if this one goes to PGL2, then this will go to PD star. Okay, and how they are related, you look at the twist, then you will have to see the, this is in PGL2. You look at Jacobi-Langland correspondence, it will become a representation of PD star, which is in this side. And then you are taking a twist by the quadratic character. So this theorem describes how tau and tau a, they are related in terms of theta correspondence. And I want to, let me go back a few slides back here. As I was saying that I want to describe this restriction. And then I will have to know what are these tau is. And I am using this theta correspondence and Walsh-Purgey involution to say when they go to PGL2 or when they go to PD star, and I will utilize those properties to talk about what is the multiplicity. Okay, so that I have written here once more. And of course, as I was saying earlier, that multiplicity is going to be all those a such that tau a is isomorphic to tau. This I have already explained. And the earlier theorem, if I use the earlier theorem, if tau is equal to tau a, meaning they will, tau and tau a, if they are same, they will have to be in the same domain. No, here the first one, it will have to be satisfied. So this is what have been written here. So then this should happen, and chi a of my, so this condition also forces us to have this -1 value of the character to be plus. So this is how we will count the multiplicity. So let me write it in other words, that what is multiplicity? Multiplicity is the cardinality of those a in this f star modulo f star square, such that this happens, which I have written here, and chi a at -1 is plus. Okay, but how to find out these numbers? How, what information this set gives? Of course, this is a very, it looks very abstract, but if you reinterpret, then this is related to the cardinality of the L packet of the representation of PG. I mean, L packets for the representation corresponding to PG, representation. So if you don't look at this condition, let's say for the moment, then this number, this multiplicity, is either going to be the cardinality of the L packet of SL2 determined by this theta tau, either it is going to be this cardinality or half of it, because you don't know whether all characters satisfy this condition or not. If all characters satisfy this condition, then this number is going to be nothing but the cardinality of the L packet of SL2 corresponding to theta tau. If those chi for which this happens, meaning you quadratic twist is not isomorphic, and but quadratic character at -1 is not equal to -1, then you get only half of it. So this is very, I would say, very important observation, that multiplicity is either going to be the cardinality of the some L packet. I'm not saying what is the cardinality here, exact cardinality, but the cardinality of the L packet from it is known that it is either 1, 2, or 4. Okay, so in our case, the multiplicity what we are attempting to count, it is either 1 or 2. So because it is going to be half of, so sorry, 1, 2, or 4. Okay. So in the beginning, so this also includes the characteristic 2 case. In the beginning, we, for example, this does not tell you how many tau and tau A are going to be isomorphic. But now we can say that this tau A isomorphic to tau, that number will be either 1, 2, or 4. Okay, so if one has to be, if you want to be more precise, and then so by the way, how much time do I have now?
Yeah. So 5
Actually,
minutes
you can-
more.
yeah.
5 minutes more. Okay, so I will. I have maybe this page and one more page. So I thought if it is over, then I might skip it. So okay, let me tell you also this. So sort of 1, 2, or 4 answer we have already got, but one can be a bit more precise. But for that we will need to relate it to the Walsh-Fuselian evolution. So now I consider only a discrete series representation of the same. Okay. So suppose tau is discrete series, because this if you take a discrete series representation, it is that set where Walsh-Fuselian evolution is defined. So let's I be a non-trivial character, because I am going to use theta correspondence, so I'll have to fix this character. I'm assuming that this discrete series representation, it is by theta correspondence, it goes to PGL2, meaning theta of tau is a representation of PGL. So I'm assuming this. Then there exists some A such that you take the twist of A, you get the Walsh-Fuselian evolution. So here tau W is the Walsh-Fuselian evolution of tau. So this is, I mean, the Walsh-Fuselian evolution is just simply a twist of your given representation. Sometimes, and the exact condition is if this twist is same, meaning you look at the theta correspondence, you write that to be pi. This pi is self-twist by chi A, and with this extra condition that chi A at -1 is -1. If this happens, then this particular twist is nothing but the Walsh-Fuselian. This is the final relation. And using this lemma, you can say a bit more precise results. So you consider a discrete series, and you look at twists of tau A, and the twist of the Walsh-Fuselian. Okay, call that this set, cardinality of this set to be M1. And since I'm relating it to the cardinality of L packet, and if you write the cardinality of the L packet determined by this representation theta tau, and then this M1 and M2, if you write down them in a correct way, then you get this close. So it depends on what I'm writing here. This lemma, and earlier I wrote a theorem of Walsh-Forge. Let me just show you. Yeah, this theorem. Combining this theorem and this lemma, you get this this identity. It gives you a very fair idea like how big this set M1 can be. And if it is a, so this was for discrete series. And if theta tau, you look at theta tau, if it is a principal series representation, then you know that you don't have tau w in that case, because there is no Jacob-Langevin correspondence. So you don't have this part here. So you have only tau of. You call this set to be M1, and again M2 be the cardinality of the packet corresponding to theta. Then M1 into M2 is nothing but this cardinality, meaning index of F star not F star square. So in particular, let's say if F has odd residue characteristic, then this number is 4. Okay.
So
And why I am describing this set, of course, once you know this set, then you will know multiplicity of tau. It is not equal to this, it is this number divided by M1. Yeah, okay, let me stop here. Yeah, thank you for your attention.
thank you, Shiv.
Thank you.
Very nice
Thank you
talk.
for speaking. Yeah.
Thank you. So
Yeah.
if there are any questions, I will be happy to respond.
Yeah,
Sure.
I have a couple of questions.
Sure, please go.
So Shiv, instead of taking SL2 over F, SL2 tilde over, if you take ring of integer, and if you want to study the same thing, so what will be the, means if you take the smaller subgroup of SLH, GL2.
Yeah.
So
So
sorry.
you are going to restrict to some compact subgroup, no?
Yeah, there will be filtration, no? So
yeah, correct. So yeah, you know, here then multiplicity is not bounded. So that is one problem in that case. For example, if you take even the linear group, when you restrict from GL2 to GL2O, or GL2, let's say GL2QP to GL2ZP, then multiplicity is not bounded. Although you know that this multiplicity is finite because of the representation being admissible, but that multiplicity it is not uniformly bounded. Here it is bounded by this let's say either 1, 2, or 4.
okay. And one more question is instead of GL2, GLN, is there any similar?
Well, see here, here is the thing. So, of course, question perfectly makes sense. There is no doubt about it. You can consider that question, but these techniques which I have been using here, that you cannot apply because we don't have, let's say, theta correspondence on SL3.
Okay.
Okay, theta correspondence, although here I wrote SL2 tilde, but theta correspondence in general should be thought of as a representation from the metaplectic group, meaning cover of symplectic group, not SLN, but SP2M.
Yes, and I think Jekyll-Langdon correspondence as well.
Yes, correct. Jekyll-Langdon correspondence is another thing we can use.
Yeah.
Otherwise, you know, as I was mentioning, in the beginning, it is not clear whether, meaning I'm getting this uniform bound, like it's either 1, 2, or 4.
Yeah.
No, this knowledge is coming from some other big work of Langlands and Love's, that if you restrict a representation of GL2 to SL2, there can be at most 1, 2, or 4 irreducible time.
Yeah.
So that's how I get this 1, 2, and 4.
Okay. Thank you, Shiv.
Yeah, thank you. Some more
muted.
questions?
Sir, your audio is off.
Oh, okay. Sorry. Yeah, I was saying if there are any further questions, please feel free to ask. Yeah. If not, then let us thank Professor Patel again. And we will be
Thank you.
resuming
Thank you
in
so
10
much.
minutes from now. Yeah. So at 3:10, we will start. Thank you.
I will stop sharing now.
Yeah.
Sure.
Do you have the hunger to build your dreams, to make them come alive, to challenge yourself, and to evolve as a champion? Welcome to SRM AP.
It wasn't long ago when I joined SRM AP. It was my first day about 3 years ago when I stepped my first foot on this campus, extremely nervous and confused about how my life is going to shape in this university. However, I was astonished by the people that I met on campus, people that come from such diverse backgrounds, people that have done so much, and all of them share one love for technology.
It's like for every 10 students, there's one faculty, which helped us develop a bond with the faculty and led to personal mentoring.
From internationally trained faculty to world-class infrastructure and practical learning curriculum, SRM AP is the one right stop to shape your future. The students from our maiden batch have emerged as successful entrepreneurs launching RI.ai with an investment of about $120,000.
SRM has given us a plethora of opportunities for us to pursue. From startup semesters at UC Berkeley to multiple international hackathons, that has helped us travel the world and reap the benefits of a large network and really get out there and put ourselves and make a mark.
There are students who are building industry level projects right out in college in the first and second years. I haven't seen people outside who probably build this scale of projects and actually get this executed and deployed in industry.
Getting a job at PVP Japan, a strategic partner of Google Japan, was really a dream come true. The curriculum at SRM University AP is a perfect blend of both theory and practical knowledge. They mold us from being mere students into very good professionals. We were the first cohort from SRM AP to visit the University of California, Berkeley. When we started participating in competitions and hackathons, we were winning against students from Harvard, Stanford, MIT, students from UC Berkeley itself, and these experiences made us break down all our mental barriers.
We provide a wide range of opportunities for our students and facilitate them to pursue higher studies at top QS ranking universities across the globe with scholarships.
I am Sriharsha.
I am Rahul.
Hi, this is Harini.
I got an admit at New York University with a scholarship of $16,000.
I got admitted to University of Michigan with a $26,000 scholarship for my whole course.
I have got admission in University of Texas Arlington.
Everybody has something to offer here. Everybody has ambition. SRM AP acts as a catalyst to your passion, be it entrepreneurship, higher studies, or placements.
Here at SRM AP, you can be whatever you want to be. If you are a dreamer, this is the place where your dreams are nurtured and encouraged.
SRM AP. Embark on the avenues of excellence.
Stephen, are you there?
Yes, I'm here.
Hi.
Hello. How are you?
Yeah, doing good. Nice to see you.
Yeah, nice to see you also.
Can we check your slides? I mean, can
Yeah.
you share your?
I will share a moment. Hmm.
Yeah.
Yes. Maybe I should.
Is it L alpha?
Yeah, alpha. Mhm.
Yeah.
So, yeah, that looks better.
Yeah.
Yeah, I think that's okay, right? Mhm.
Right. Thanks.
Welcome.
So how are things there? Can you hear me? Yeah.
Yes.
Okay. No, I was just asking, how are things there back in Belur?
Oh, I didn't hear that. Okay.
Okay.
Yeah, we are in full online mode.
Right.
But
So this
probably by the end of the year we will be we will return to normal teaching. There was normal teaching in between in the time when it was quite good. So in February, but now at the moment it's not possible. Mm-hmm.
Yeah, same here. We are also having online teaching until December at least. So.
Yeah. Oh yeah.
Right.
And are you vaccinated?
Yes. I had both doses.
Good, yes.
Yeah. Right.
Yeah, in normal times there are always big crowds coming to Belmont. Now there's nothing here. It's very quiet here. Very unusual compared to earlier times.
Yeah, right.
Mm-hmm.
So we'll wait for a minute and then proceed.
Yes. Mm.
Okay, so welcome back, all of you. So we'll proceed with the second talk of this session. It will be given by Professor Stephen Beyer, and he'll be talking on distribution of L alpha modulo 1, where L runs over the primes. Over to you, Stephen.
Okay, thank you for the nice introduction, and to the organizers for inviting me here and giving me the opportunity to give a talk at this nice little conference. Yeah, I give a talk which is kind of a combination of two talks which I gave recently, one at the Balu Fest and one at the Subarao colloquium, or Subarao symposium. in Pune recently. Okay, it's about the same topic, but yeah, two topics basically. I mean, two subtopics combined: the number field case of the problem and the p-adic case of the problem. So it's about the distribution of L alpha modulo 1, where L runs over the primes, alpha being an irrational real number, and the extensions of these problems to number fields and the p-adic setting. Yeah, I used here the letter L because yeah, usually one would use P, but P is already used for p-adic, and that's a different P. So therefore, I use the letter L here. And so this is joint work with several authors. So different results have been worked out with different authors. Vaipan Mazumdar, that's a PhD student at our place. Sudhir Pujari, and Mark Techner. Okay. Starting point is one of the most basic results on Diophant approximation, the Dirichlet approximation theorem, which has the following consequence. If alpha is an irrational real number, then there exist infinitely many pairs of integers, AQ, such that AQ are coprime, and alpha is approximated by the fraction A divided by Q in such a way that the difference is bounded by Q to the minus 2. That's very easy to prove using pigeonhole principle or explicitly using the continued fraction expansion of alpha. There's also a proof using Minkowski's theorem. And anyway, it's very easy to prove. An equivalent formulation is like that. If we have a irrational number alpha, then there exists infinitely many Q, such that, sorry, can I somehow, yeah, okay. So that the distance of Q alpha to the next integer is bounded by Q to the minus 1. So this function here denotes the distance to the next integer. Yeah, you obtain that just by multiplying the above with Q, this inequality alpha minus A divided by Q, less or equal Q to the minus 2. If you multiply this with Q, you get the equivalent formulation. So now that's easy to prove, but it becomes much harder if you restrict your set of Qs to, let's say, an arithmetically interesting set of integers, like, for example, the primes. So that's what this talk is centered around. This question has received a lot of attention and generated a lot of interesting mathematics. Okay, so the question precisely is, let alpha be an irrational number, for which exponent tau can we prove that there exist infinitely many primes p, such that the distance of p alpha to the next integer is bounded by p to the minus tau plus epsilon for every epsilon greater 0. So it has a reason why I included this epsilon, because so the expectation is that this result holds, or that we have infinitely many such primes for tau equals 1. So the same exponent like in the Dirichlet approximation theorem, but with an extra epsilon. So it's not possible to remove this epsilon completely. One can see that by a result of Harman, who proved that there exist irrational numbers alpha. So he constructed irrational numbers alpha, for which one cannot do better than showing the infinitude of primes, such that the distance of p alpha to the next integer is bounded by constant times log p divided by p log p. So that's larger than 1 divided by p. So therefore, if one formulates the question with just one exponent, one needs an epsilon here. What is proved is very far away from this expectation. So one knows the result to hold under GIH for tau equals 1/3. That's actually easy to prove. So one can boil down the problem to a problem on primes and arithmetic progressions in unions of arithmetic progressions. And so then one can use, directly, so one can detect these congruence conditions using Dirichlet characters and can boil down the problem to counting primes, to Dirichlet L functions. Okay, so that's not hard. It's much more difficult to achieve this exponent unconditionally. This is actually also known to hold. So tau equal to 1/3 is also been achieved unconditionally by Matomeki. So that's the current record. Use a lot of technology, sieve methods, Klosterman sums, and so on. To go beyond 1/3 seems to be very difficult. So it depends on very strong hypotheses about primes and arithmetic progressions. So that's really the limit of the current technology, this 1/3. Good, let me first recall the history of this problem. Vinogradov considered it already. He obtained an exponent of 1/5. That was sometime in the 30s of the last century. To this end, he used his non-trivial treatment of trigonometrical sums over primes. So basically exponential sums over primes. He managed to do non-trivially, unconditionally by an ingenious kind of sieve method. This was later simplified by Rohn. He came up with his famous identity for the von Mangold function. This, together with the refinement of the Fourier analytic arguments, and Vinogradov's paper allowed him to improve this exponent to 1/4. Then a number of authors improved this result. 3/10 by Harman. So that's by his sieve method, which I will talk about later on in this talk. So he introduced the sieve method and managed to improve this exponent to 3 divided by 10. Then by an improvement of the numerical computations, Gia achieved 4/13, so it was slightly larger than 3 divided by 10. Then Harman, by a refinement of the sieve method, got 7/22, which is already quite close to 1/3. Again, Gia, by some refinements, got 9/28. Then Heath Brown entered the game, and he observed that Klosterman sums are actually helpful in the problem. So he made a relation to Klosterman sums and used thus the Weyl bound for Klosterman sums to obtain a further improvement. Actually, there are more ideas, novel ideas going into this paper. But so this is most significant is the use of Klosterman sums. 16/49, that's already very close. And so then the final breakthrough to get this exponent, which one knows to hold under GIH. This was achieved by Matomeki. What she did was to exploit averages of Klosterman sums. So she made use, what is in the background is the Kuznetsov formula, connecting Klosterman sums, averages of Klosterman sums with Fourier coefficients of mass forms. Okay. So then, so since it's very hard to make progress on the classical problem, it is reasonable to look at extensions of these problems to number fields, function fields, to the periodic setting. The first one who, actually I forgot to include one much weaker result, which I got on QI, but that's on a later slide. So Harman achieved the same exponent 7/22 from 1996 for QI in 2019 by making his method work for the setting of QI. Around the same time, Mark Technau and I looked more generally at imaginary quadratic fields. We got the exponent 1/4 of Bone, which is weaker, but we got a more general result. Then real quadratic fields were considered by Dwaipa and Mazumdar and myself. Yeah, we achieved the same exponent 1/4. So this involves a lot of technical issues which have to be overcome, which are not present in the imaginary quadratic case.
Excuse me.
Yeah.
There is a question in the chat box.
Oh yeah. Okay. Let me check. Yeah, I check.
Yeah. The question is, why do we hope tau to be 1?
Yes, that's a good question. In fact, so there's a conjecture of Lindick on primes in arithmetic progressions, the least prime in an arithmetic progression, which predicts that in an arithmetic progression, A modulo Q, with A co-prime to Q, the least prime should be of size O of Q to the 1 plus epsilon. So if one assumes that to be true, then one could show that this exponent 1 holds, tau equals 1 holds. So that's actually not very difficult to relate these two things, and then yeah, this would give 1. So what one can show under GRH is tau to the Q to the 2 plus epsilon. Yeah. Okay, I hope this answers the questions. All right. So in recent work, we actually managed to improve generalize Harman's result in to quadratic fields in general, to imaginary quadratic fields and real quadratic fields. That's a joint work with Dwaipa and Mazumdar and Mark Technau. Okay, I will say some more things about this later. Yeah. So I want to talk about our works, but to this end, it makes sense to get an idea how it works, at least in the most basic setup for integers. In particular, how Harman's sieve method works. So I will give an overview of a basic setup, which gives this exponent 1/4 of Bone, but using Harman's sieve, a version of Harman's sieve. I will not touch the Klostermann refinements and the refinement of the sieve method, which led to better exponents. Okay, just the most basic idea. In fact, we will make use of the Dirichlet approximation theorem for alpha, but this comes in at a much later stage. So since we don't have anything like GIH, we use a sieve method. What is especially suited for the situation is the Harman sieve. So the basic idea is the following. So we compare two quantities. One quantity, so this function f(ix) is the indicator function of the set of small intervals around the integers of length 2 delta. So precisely it looks like that. So it's equal to 1 if the distance of x to the next integer is less or equal to delta, and it's 0 otherwise. So then the quantity which we are actually interested in is precisely this sum. So we take a dyadic interval n to 2n. We count a number of primes such that p alpha has distance less or equal a small delta to the next integer. We may express this in this form, sum over p, fi p alpha. So now the probability that P has distance at most delta to the next integer is 2 delta heuristically. So therefore, we expect this to be roughly of the same size as the number of primes in this dyadic interval, multiplied with 2 delta. So we compare these two quantities, this quantity in question and 2 delta times number of primes in the interval from n to 2n. Okay, so what we want to show is that for delta not too small, but reasonably small, the difference of these two quantities is small. We use the sieve setup with some notation, usual notation in sieve theory. Let M be a finite set of integers, Z be a parameter. What we are interested in is the number of elements in the set, which are not divisible by any prime less or equal Z. If you want, you can also restrict the set of primes to a subset of the primes, but in this problem, we take all primes. Yeah, so we sieve out multiples of small primes. Then you can also sieve for primes in particular if you choose the parameter Z to be of size n to the 1/2, and you assume the set M is contained in the dyadic interval from n/2 to n. Okay, so then it's yeah. Simple consequence of the sieve of Eratosthenes that you get precisely the cardinality of the set of primes in the set M. So that's what we are doing here, in fact. So now Hammond sieve is a kind of comparing sieve. So the philosophy is as follows. We have two sets A and B, usually in applications. A will be a small subset of B, and we compare SAZ with SBZ under the assumption that we have good information, so we know well how approximately SBZ behaves. So for example, okay, let's go to the setup. In this particular case, so here we consider B to be the set of all integers between n/2 and n, and A to be the set of all integers in this interval, such that the distance of n alpha to the next integer is less or equal delta. So what we want to do is precisely to estimate the number of primes in the set A. So we want to get a lower bound for the number of primes in the set A. So then if you take Z equal to n to the 1/2, then SBZ is precisely the number of primes in the interval n/2 to n. And SAZ is precisely the number of primes in this interval such that P alpha, distance to the next integer, is less or equal to delta. So precisely the quantities which we are interested in. So the idea is to compare these two quantities in a certain way. And what the Hammond sieve does is to actually show that this difference is small. The difference with one quantity suitably scaled is small, provided we have a certain bounds for so-called one type and type 1 and type 2 sums. So type 1 and type 2 sums are certain bilinear sums of the following shape. So let's take A and Bn to be sequences of complex numbers, arbitrary sequences, which are bounded by the divisor function. So we have a good bound of them. Then our assumption is that certain bilinear sums, on the left-hand side, we have a bilinear sum which involves the set A. On the right-hand side, we have a bilinear sum which involves the set B, are comparable with each other. So of comparable size. So precisely what we have is on the left-hand side, we have so-called type 1 sum. So it's a sum over two integers, m and n, where m is restricted to some interval, m is less or equal to some parameter m, and the product of these two lies in A. We take the sum over am, so but implicitly the summation variable is there, summation variable n, because for every m, we also consider the n's such that mn is in the set A. And on the right-hand side, you have the same sum with A replaced by B, but the whole thing multiplied with a certain scaling factor, lambda. So we assume that these two sums are approximately of same size up to some error term, O of y, let's say. And we assume the same to work for general bilinear sums, where also there's some coefficient depending on n occurs. So m is restricted again to some interval, n to the mu, and n to the mu plus kappa. Mn is supposed to lie in A. And on the right-hand side, we have the same, but with the set A replaced by B, and the same scaling factor included. So when we have such approximations of bilinear sums for the set A by bilinear sums for the set B, with these parameters, m, mu, and kappa lying in suitable ranges, then we can deduce that the quantities which we are interested in, so the Sieve quantities, also have small difference. Okay, so this boils down the problem to actually establishing such type 1 and type 2 approximations, as in this general Sieve result. So that's the very simplest version of Harman sieve, an asymptotic sieve, where we have a asymptotic estimate in the last line. So there are lower bound versions, which are more difficult to prove, and which allow more flexibility of the parameters, and therefore potentially give better results. But let's just talk about that here in this talk for simplicity. Okay.
Yeah, sorry. Hello.
Yeah.
Yeah. Can you just point out like why that second condition, the bilinear one, is satisfied there? Because this one.
Yeah. Okay. So I don't go into the proof of that result, but so basically the idea is we decompose the Sieve quantity using an iterated application of Buchstabs identity into certain sums. So over several primes, so R tuples of primes, and we group these R tuples of primes into two. I mean, we take two groups among these R tuples. So the product of the elements of the first group will give M. The product of the elements of the second group will give N. Okay, and we need to give, yeah, so then we end up with precisely such bilinear sums. If we do like that, we just need to make sure that M and N lie in the correct ranges. So that's basically the philosophy of the proof of this result. Does this answer your question?
Yeah, okay.
Yeah. Okay. But so the technical details are not easy. One needs to be very clever to get the variables M and N in the correct ranges. Okay. Yeah, so in our application, it looks like that. So the type 1 sums are of this form. Type 2 sums turn out to be of this form here. Yeah, okay, let me just talk a little bit about that. So Mn in the set A means nothing else than Mn times alpha, distance to the next integer is less or equal to delta. So we get this summation condition for Mn is element of A. And on the right hand side, we don't have this summation condition, we just have that the product of M and N lies in the dyadic interval from n half to n. So that's easier. And we would like to show such approximations here. Yeah, to be precise. Yeah, so if we can show such approximations with suitable error term, so precisely of size delta n to the 1 minus epsilon, a little bit smaller than delta n, then we can deduce what we want actually. So then we have quantity in question is like 2 delta times number of primes in the interval from n½ to n. Good. So we may rewrite this using our function fi. That makes things a bit more convenient, which detects precisely this condition mn alpha, distance to the next integer is less or equal to delta. Good. So this function fi is a periodic function. So it's basically centered around integers. It's 1 if x is close to an integer. It's 0 otherwise. So yeah, since it's periodic, it's not surprising that to expect that we can use Fourier analysis to approximate this function fix. Good. So now for this particular function, we run into trouble when we take an infinite Fourier series development because it doesn't converge absolutely. And in particular case, yeah, there are problems at the discontinuities. So a better device is to approximate fix from above and below by trigonometrical polynomials. This is possible. There are many such results in the literature. In particular, a result like that holds if delta is less or equal to 1/4, which we can assume. And L is some natural number. Then there exist 2 sequences of complex numbers CL plus and CL minus, such that fix is bounded from above by 2 delta plus a small quantity plus a trigonometrical polynomial of length L square with these coefficients CL plus on the right hand side and the coefficient CL minus on the left hand side. So this 2 divided by L is a disturbing summand, but we can choose L large, so then this becomes small and doesn't cause any trouble. Important is that we have here the 2 delta, which should come up, because yeah, if you take the Fourier series development, then the constant term is 2 delta. So that's precisely the integral of the function on an interval of length 1. Okay, and we have good bounds for these CL plus minus, so it's bounded by delta and also by 1 divided by L. Okay, so now, yeah, we make some more technical manipulations to bound our type 1 sum. So here we have complex coefficients AM. We split that into imaginary part and real part, and then the imaginary and real parts again into positive, contribution of the positive elements of the sequence and the negative elements of the sequence. So in the end, we can boil down the problem to this problem here. So we want to, I remind you what we want to do is we want to show that the right-hand side is approximately equal to 2 delta times the same sum without this FIM alpha. Okay, we want to remove the FIM alpha basically. Replace it by 1 scaling factor 2 delta. So we need to approximate this, or we need to bound this sum on the right-hand side of the first equation on this slide from above and below. So since we have split these AMs into imaginary part and real part, and then further into the contribution of the positive elements and the negative elements. We can restrict ourselves to the case when AM consists of when AM is a sequence of positive real numbers or non-negative real numbers. Okay, and then we can using this previous lemma, which gives a bound for Fix, bound our sum in question from above and below. So what we see here is the sum over L and the sum over M and the sum over N of this form. So a trigonometrical bilinear sum. Actually, it's even a trilinear sum if we write it up like that, because we have three variables M, N, and L. So now we take our L suitably, a little bit larger than delta to the -1. Remember, delta was very small. So then we want to show a bound like that. We want to show a good bound for this trilinear sum. If we are able to do that, then we get a desired approximation. So now in the case of these type 1 sums, we make use of the fact that the sum over n is smooth. So this sum over n is there. If we fix m, then n runs over some interval, dyadic interval of the shape. So it's from n divided by 2m to n divided by m of E of L, M, N, alpha. So that's a smooth exponential sum in n, which can be estimated by standard estimates. So this standard estimate here. From that, we immediately deduce some estimate for the trilinear sum of this shape here. Okay, so here the distance of L, M, alpha to the next integer comes into play, where L and M run over certain intervals. So we want to make use of the fact that often this distance is to the next integer is large. So that this term, distance of L, M, alpha to the next integer to the -1 is often not too large, which is often, is often small. Okay, so I don't go into the detail, but so this can be done by a relatively simple counting argument. So what we need to bound precisely is the sum of this form here. K runs over some interval, and we want to bound the sum of minimum y and this inverse of the distance of k alpha to the next integer. Trivial bound would be just k times y, if we take y in the minimum. But often we can expect this second term in the minimum to be much smaller than y. And so what one does here is basically one approximates alpha using the Dirichlet approximation theorem. So now this Dirichlet approximation theorem comes into play. And then, then the problem becomes simpler. So one basically replaces alpha by a fraction a divided by q, which is nearby alpha, and observes that the same term with alpha replaced by a divided by q behaves similarly. So then it's very easy by the counting argument, involving residue classes modulo q, to deduce a bound for that. Of course, we need to choose q in the correct range, so it should not be too large, otherwise this bound gets bad. And also, if it is too small, it gets bad. Because, I say the trivial bound for this is ky. If k is small, then we get a saving by a factor of q. So if you multiply out the brackets, then most significant is the term y times k divided by q. So we save the factor of q over the trivial bound if q is in the correct range. Good. Yeah, so this is now a matter of calculations, but is all straightforward. We can now get putting everything together, a bound for the type 1 sums. So the type 2 sums are more difficult because here we don't have a smooth exponential sum. So I remind you to this sum. Yeah, it looks like that here, the type 2 sum. So we have two coefficients, a and bn of general shape. So we don't have any control of the precise shape of these coefficients. So what one does in these cases is one removes one of them using Cauchy's inequality, then expands the square, modulo square, and moves in the outer summation. Then artificially one produces again a smooth sum. So basically, the idea is to remove one of these coefficients using Cauchy-Schwarz. But of course, by using Cauchy-Schwarz, one loses a lot. But this is not avoidable. In some form, one needs to use Cauchy-Schwarz here. And yeah, good. But then after doing that, one can use similar arguments. Good, there are some more technical things. And then one needs to optimize the parameters. So we had in our sieve result the parameter mu, which is some exponent. Then we have some q, which we need to choose. And yeah, so finally one will obtain precisely, one will recover Vaughan's result using this simple setup of Harman sieve. As I said, refinements of this lead to better exponents. Then using more ideas than just sieves, Klostermann sums in particular, one can make further progress. And finally, Matomeki pushed it to the limits method. So now I have talked already very much about the classical setup. It's better to focus on that part because at least, yeah, for people who have not seen that talk, so they can get an idea of how these methods work. So I will rush a bit through the number field case and just indicate where the additional difficulties come from. So it's by far not straightforward. In particular for real quadratic cases, real quadratic fields, things are much more difficult because here we have to deal with yeah, the infinitude of the unit group in particular and other technical issues. Yeah, and so far, in fact, there are only results for quadratic extensions. So nobody has looked into higher degree extensions of Q. So we will assume throughout, or we assumed in our papers throughout, that the class number is 1. That makes things easier. However, this restriction should not be essential. So with additional care, it should be possible to remove that condition. So one can say that the imaginary quadratic case is relatively close to the classical setup, but the real quadratic case is more involved. As I said, one has to deal with the infinitude of the unit group. And also, it becomes a truly two-dimensional problem, which leads to actually a counting problem in the end, which is of very much different flavor. Okay, some overview of results. So I got a much weaker exponent than Harman, but for a more general result, where the Gaussian primes are restricted to sectors. So I got this result for Qi. So then Harman proved, yeah, a result on Qi with the exponent 7/22 in 2019. So yeah, I mentioned that already in the beginning, actually. And I don't need to say that again. Okay, 1/4 for imaginary quadratic fields was Mark Tegner and me in 2020, and then in 2021 for real quadratic fields, the same exponent, and now we have the exponent 7/22 for quadratic fields in general. One may hope that one can also push the exponent to 1/3. That may be difficult, but actually, Dwight Byrne, this PhD student of mine, looks into that problem for QI right now. Okay, let's first look at the imaginary quadratic setting, and just let's restrict to QI because it's the simplest case, and so the more general, the general case of imaginary quadratic fields of class number 1 is similar. So let's just look at QI and let's see which difficulties occur here. So the correct setup in the setting of QI is we take some complex number which is not contained in QI. So then by this norm function, we denote the distance of z to the next Gaussian integer, so to the next element of OK in this case. So we can take either the distance, and we can take the distance in any norm, in particular in the supremum norm, which would be then maximum of distance of real part of z to the next integer, and distance of imaginary part to the next integer. Okay, so then one can use a similar sieving setup. So here, in general, for a finite subset of the string of integers not containing 0, we define SMZ to be that should be a cardinality of the set of all elements of the set M, which are not divisible by a Gaussian prime with norm less or equal z. Basically the same, just we need to include the norm here. So then Harman proves this result below, the complete analog of this result for the integers, for the integer setting of the problem. Okay, so distance of p alpha to the next Gaussian integer is infinitely often bounded by modulus of p to the minus 7/22. Okay, so then we use also, or one can use Harman sieve. Harman makes this method work in this setting. So then one considers similar sets A and B, but these are now Gaussian integers in annuli. So the norm of n is between n½ and n. Okay. So then, I will skip some details here. So one can formulate, or one can prove in a very similar way an Harman sieve in the fields or in the setting of Gaussian integers. And so now the problems occur already at the Fourier analytic part. So instead of our function Fix, we need a doubly periodic function, which is precisely the product of Fi real part of z and Fi imaginary part of z. So to detect complex numbers close to Gaussian integers. So now previously in the one-dimensional setting, so in the setting of integers, we had a lower and an upper bound of Fix in terms of trigonometric polynomials. So now one needs to be careful already with the lower bound, because it may happen that Fix is equal to 0 and Fi minus x is less than 0. So, and then it's certainly not true that Fi real part z times fi minus real part z times fi minus imaginary part of z bounds fix from fiz from below. Rather, what one has is a bound of this form here. So it's a little bit tricky. So this function fi cos I z, which one needs to bound from above and below, is bounded in a simple way from above by the product of fi plus of the real part and the imaginary part. But in a more complicated, we have a more complicated bound from below. Okay. Good. So anyway, the same procedure as before leads again to trigonometrical sums, but now taking over Gaussian integers of this form here. So now in the exponential, the imaginary part of k and alpha occurs. One technical issue which occurs is that these sums are over annuli. So in particular, the inner sum is over an annulus. If we had a sum over a rectangle, things would be much easier because then we could break up this sum into two one-dimensional exponential sums and use the classical bounds for these one-dimensional exponential sums. But we have a more complicated region, so the geometry of the region comes into play, and we only have a weaker bound in this case. So when you have a product of two intervals, then you get a good bound, but you get a weaker bound for if you take an exponential sum over an annulus. So Harman finds a way to settle that problem, basically again reducing the problem to a one-dimensional problem. I don't want to go into that detail because there's not so much time left, or there's very few time left. So yeah, so now I need to, so how much time do I have actually?
So Stephen?
Yeah.
Yeah, it is until 4. So I mean, if you
until 4. Yeah, so then I will put
it's more as well if you want.
But this is not a problem. I will just rush through that. So
okay.
I think most important is to get some idea of the classical setting. Okay. Good. So basically, I just tell you the idea. Mark Techner and I, we take a different route. So we avoid a lot of technical problems by completely smoothing out the problem. So instead of sharp cut-off sums, we take weighted sums. So we weight the thing by a Gaussian. So we weight both, we smooth out both. Yeah, the sum taken over all primes in the interval from n½ to n. So this becomes a smooth sum. And also we smooth out our function fi, that in the two-dimensional setting here. So that's quite elegant to do that because this allows a conveniently to use later in the process the Poisson summation formula without error term. So we smooth out the whole problem, and we prove also general sieve results, versions of Harman sieve with a smooth weight function. So that's basically the idea of our approach. That makes things much more elegant. We do a similar thing in the real quadratic setting. So yeah, so now I cannot say much about that. Okay, all I say about that is that now we have a two-dimensional problem. In fact, but we do a similar smoothing procedure in the real quadratic case. Then so we have to deal with a lot of technical difficulties, which makes the definition of the smooth weights particularly complicated. But in the end, we can again use a Poisson summation formula in a convenient way. The important thing which is different from the setting of imaginary quadratic fields and the setting of Q is that at the end we encounter a certain two-dimensional counting problem, Diophantine counting problem with a matrix. So if you remember when we talked about the integer setting, we encountered in the end a certain counting problem where we made use of the Dirichlet approximation theory. So here we encounter a two-dimensional counting problem, and we use a version of the Dirichlet approximation theorem for our real quadratic field, which is a two-dimensional version, in fact, dealing with the two embeddings. Okay, so now one interesting thing happens, which is not present in the case of imaginary quadratic fields and of Q. So the bounds which we get in this counting problem depend in a certain way on results about roots of quadratic congruences. So we make use of results of Houle about the distribution of roots of quadratic congruences. That's a quite interesting feature which shows up in this real quadratic setting, which was quite surprising to us, but it seems to be genuinely connected with the problem. Okay, I will not go into that detail, and just I remark in the end, recently Sudhir Pujari and myself also considered some p-adic version of the problem. So in this case, there's also a reasonable function which replaces this distance function. One can ask a similar question as before, and this boils down quite straightforward to counting, estimating the size of the least prime in an arithmetic progression to a prime power modulus. So there's a general result about the least prime in arithmetic progressions due to Psiloris. That was mentioned actually in the first talk by Professor Balasubramanian. But specifically here we need prime power moduli, and there are better results in this case when we restrict to prime power moduli. So using a recent result by Banks and Spalinski, one can prove a certain much better exponent than in the integer setting for the p-adic setting. And so here we have the goal to actually improve that a little bit. But I have no time to go into that. Okay, I talked about this in Pune at length, this p-adic analog of the problem, and some results related to that. Okay. Good. So then, I'm sorry for I'm sorry for the delay, and thank you very much for your kind attention.
No problem. Thanks very much, Stephen, for a very nice talk. Any questions?
Yeah, one thing I will ask, like, so how do you deal with that summation over L in the, like, when you were taking this, there was the summation over L, M, and N. The N sum was dealt with the smooth sum, exponential summation. M sum was the Diophantine approximation. But there was
in fact, that's a good question that I can tell. Moment, I go back to the slide. Here it comes. So you are talking about the sum, certainly. So this trilinear sum. So what we basically do is we divide this L range into dyadic intervals and put together the L and M. So we take that LM to be K, and then where is it now? Yeah, so then we are down to such sums, which I put here on the slide. Yeah, so we put these together. And we just estimate these coefficients which occur using this bound for CL and the divisor bound for the other coefficient. So that's just an upper bound in this case.
Okay.
Yeah.
Yeah, and the another thing is that, yeah, sorry. The another thing is that when like the smoothing thing you were saying, so you mean instead of that cutoff function that which was one whenever the distance was less than delta, instead of that you were using a smooth function over that interval?
Yeah, precisely. I had not enough time to explain that, but I can do in response to your question. So we take that function basically. So this is close to 1 if this theta is close to an integer. So here inside is a Gaussian. And if theta is spaced away from every integer, then it becomes small. So it's basically what it is a shifted theta series. Shifted by this.
Yeah, so here no need to look out for any kind of Fourier expansion. Directly we use this particular summation itself with this summation n. That would be.
Yeah, precisely. And so here we can use Poisson summation directly to convert this into a different, which makes things very nice actually.
Okay.
Yeah.
Thank you.
Yeah, welcome. Yeah, in fact, so this is the Fourier expansion, and the nice thing what happens is so that's it. Yeah. That is rapid decay.
Any further questions? Okay, if not, let's thank Stephen again for a nice talk.
Thank you very much.
Yeah, thank you, Stephen. So the next talk will begin in 12 minutes at 4:20.
Good, I stop sharing. Stop share. Okay.
SRM University, Andhra Pradesh, Amaravati was born to offer a unique learning experience, to deliver cutting-edge education, to foster innovation and to create the leaders of tomorrow. Sprawled over 200 acres, the university has been designed by the world-renowned architecture firm Perkins & Will. The lush, green, eco-friendly campus provides a conducive environment to learning and creativity. SRM University, Andhra Pradesh, Amaravati is a multi-stream research university with focus on diverse fields including engineering, medicine, liberal arts and management. It offers a rich selection of graduate and undergraduate programs across faculties. What's more, the faculty is highly qualified, experienced and has global exposure to mentor and support the students every step of the way. In a bid to accomplish research excellence, SRM University, AP Amaravati offers pioneering research under subject experts and thought leaders.
Hi, so this is our computer lab, one of the most modern labs across India. We've been doing so many projects across here, and with the amazing faculty support, you can do wonders here. These are all wonderful modern systems.
Research is an integral part of SRM Amaravati and spans engineering, science and liberal arts. To foster a culture of research excellence, the university integrates research in the undergraduate curriculum through Undergraduate Research Opportunities Program. The university is setting up centers of excellence in areas such as artificial intelligence and machine learning, renewable energy, meta materials.
This is a place where we work on bleeding and cutting edge technologies, avoiding time sinks and focusing on innovation. With our work, we have also been awarded the Reimagine Education Silver Award awarded by Wharton School of Business and QS.
50% of our lab members are women. We have also organized events which will foster the spirit of programming in women who have never programmed before.
The university is equipped with a cutting-edge NextTech laboratory. It holds the proud distinction of winning the maximum number of hackathons in India. The university is currently working on developing a hydrogen fuel cell-based train. SRM Amaravati's board members comprises of leaders and industry from across the globe. ensures global exposure for its students by collaborating with some of the world's most eminent universities. MIT US, UC Berkeley College of Engineering, IIT Chicago, and EFREI, to name a few. Boasts of excellent infrastructure and resource availability, including AC bus service, round-the-clock ambulance services,
Hello.
Hello,
Yes.
Dr. Acharya? Are you
Hello,
there?
Sandeep.
Yes. Are you there?
Yes.
Yeah, can we check if your slides are displaying properly here?
Sure. By the way, am I audible enough?
Yes.
Yes.
Yeah. Yeah, you see the full screen? No. Yeah.
So it is not cooperating.
Okay. You mean the full screen thing?
Yes. This is not cooperating. Follow it. So, I mean, is it fine? Yeah.
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 Should be.
How are you, Ratna?
Fine. So you?
Yeah, fine. So are you in Srirampur now?
Yes. And in fact, my locality has been flooded.
Oh.
That's why the connection is also little poor here.
Okay.
And it's not possible to go to Belur these days.
So when you went there last time?
Couple of weeks before, I mean, around around 15th, I guess.
Okay. Should we begin?
Yes.
Sorry.
Yes.
Okay, so it's my pleasure to welcome Dr. Ratnadeep Acharya to give the final talk of this conference. So he'll be talking on continued fractions, rational approximation, and certain exponential sums involving the Fourier coefficients of cusp forms. Over to you.
Thank you for the introduction. And also, I'd like to thank the organizers for the invitation here. It's my pleasure to speak in front of you. As you can see, the title of my talk is Continued Fraction, Rational Approximation, and Certain Exponential Sums Involving the Fourier Coefficients of cusp forms. So it is perhaps the longest title in this conference, I guess. Okay. First, I'll discuss cusp forms. Then, what are the Fourier coefficients of cusp forms. And these things has already been discussed in this conference, first by Balesh yesterday and today by Karamdev. And next, I'll discuss what is our goal today. I mean, what kind of exponential sum we are going to study. And next, what are the basic results for such estimations. And then finally, we'll talk about some recent development based on continued fractions. Okay, let me start. So holomorphic cusp forms. So the modular group SL2Z, you are all familiar with this, that acts on the Poincare upper half plane H by the rule that gamma Z is AZ plus B over CZ plus D, where A, B, C, D is a matrix in SL2Z. So by holomorphic cusp form of HK and level 1, we mean a holomorphic function F on the Poincare half plane satisfying following conditions. Number 1, the orthomorphic condition. It tells about certain transformation rules under the action of this group SL2Z on H. This is given by this, where J gamma Z is CZ plus D. Next one is the cuspidal condition. It tells that if imaginary Z that goes to infinity, then the function JGZ, as you can see here, what is JGZ, is the denominator of the action, times to the power minus k times f of gamma Z, that will go to 0. Well, so that, I mean, what is this condition is known as cuspidal condition. I'm not going into the details, but note that this I infinity is the only cusp for SL2Z. For general level group, I mean, for general level N, similar forms can be defined with much more effort, but for this talk, I'm going to concentrate only on level 1 case. And in that case, the only cusp is at I infinity. So for, level 1 cusp form, these two conditions will suffice, and also the holomorphic. Okay, fine. Next, what are the Hecke eigenvalues associated with these forms? Let SK1 space of such cusp forms is defined just right now, and any form F in SK1 that admits Fourier expansion of that type. Here, this lambda Fn denotes the normalized nth Fourier coefficient. Okay. And again, I'm not going to define what is Hecke operator. It's also been discussed in Balesh's talk yesterday. So if, these Hecke operators are certain operators acting on the space of cusp forms. So if F is a Hecke eigenform, then F is basically a simultaneous eigenfunction for all the Hecke operators. And in that case, the Fourier coefficients lambda Fn coincides with the eigenvalue of the nth Hecke operator. And the normalization is done in such a way here, so that this coincidence occurs. So now will list some properties of these Hecke eigenvalues or Fourier coefficient, whatever you call it. So first, these are real. So remember that I'm considering only the level 1 case. In that case, the Hecke eigenvalues are real. Secondly, these are Hecke multiplicative. So that means there is the rule that lambda fm times lambda f of n is given by the convolution sum where d divides the GCD of mn, is lambda f of mn over d square. So in particular, so lambda f, I mean, viewing as a arithmetic function, this is also multiplicative. You can note that. Third one, so the Delling's bound helps us to, I mean, is given by that one, is that lambda fn is bounded by the divisive function, and it was proved by Delling's, and basically it, I mean, also you can view it as that lambda p, I mean, where p is prime, is bounded by 2. So just look at these 3 properties. So thus you can see that the Hecke eigenvalues gives rise to an arithmetic function of particular interest. And in analytic number theory, the randomness of arithmetic function has been one of the, I mean, central objects to study. And here, we are considering such things for the particular arithmetic function lambda f of n. Okay. Next. So what kind of exponential sum we are going to discuss? First, the unrestricted sum. Unrestricted sum SF x alpha, as we denote it, is nothing but n up to x lambda f of n times e of n alpha. So it is known due to Jutila that this exponential sum admits the upper bound x to the half. Moreover, this bound is best possible. Why is so? Because, I mean, you can note that if you consider the integral 0 to 1 s of x whole square times d of alpha, then it will be by the, I mean, orthogonality of additive characters, it equals to n up to x lambda fn whole square. And it is known due to by the Rankin-Selberg method that this sum is equals to c of fx plus big O of x to the 3. And this constant depends only on f, nothing else. So, I mean, you can say that this is squared. So that, in fact, the second moment, so the maximum one can expect is for the size of SFX alpha is the square root of x, what is done by Jutila. Fine. Next, well, as we use the notation here, is that the notation of big O, we must stop. What is that? That for any two complex valued functions f and g, you can write f less g or f is big O of g if this happens, that fx is less than equals to some constant depending only on a times g of x for all x. Fine. Now, so instead of the unrestricted sum, we are going to discuss two different type of exponential sums. type 1 exponential sum is that when instead of considering all the integers, if we consider a sparse subset of the natural numbers, for example, primes. So yes. So in particular, we define the sum Pf of x alpha is given by sum over n up to x lambda fn, capital lambda n, E of n alpha. I'm going to define what is capital lambda n. This is the von Mangold function. Is given by log p if n is a prime power and 0 otherwise. So basically this is supported on prime powers, but in practice this lambda roughly acts as an indicator function in the set of primes. Note the prime number theorem for Hicke eigenvalues also. So this is given by that one. Lambda fn times n is less capital X times exponential minus c square root of log x. Well, the saving here is much bigger than any power of log x. Yes. And what is exponential sums of type 2 here is that, so the problem becomes more challenging if we twist the sum by another oscillating arithmetic function. An interesting example is that if the arithmetic function is the Mobius function, and the sums we need to consider is that is denoted by mf x alpha. This is n up to x lambda fn mu n times e of n alpha. And the Mobius function is defined by this. At n is equal to 1, it is 1. If n is product of k distinct primes, then it takes value -1 to the power k and 0 otherwise. So let us recall what is Mobius randomness law here. So the Mobius function changes its sign. You can say from here the definition also, that the Mobius function changes the sign frequently often, so that any reasonable sequence an, for that the defined twisted sum is sum over mu n times an is relatively small. That means there are sufficient cancellation in that twisted sum. So keeping in mind that, we expect much cancellation in that sum mf x alpha. Okay, so these two are my object to study here, pf x alpha and mf x alpha. So that means lambda fn mu n or lambda n times e of n alpha. Okay. So before stating the result of Fugri and Ganguly in this direction, so what follows from the second moment of the Fourier coefficients lambda fn is that for almost all alpha belongs to R, we have pfx alpha and mx alpha, both are less square root of x times log x. So in fact, for mf x alpha, for that one, this log x can be removed. Okay, so these estimates are strong enough. However, the problem is that you don't know for which alpha you have such some strong bounds. Not a single alpha. I mean, at least from the Rankin-Selberg method and the estimate, the integral, second moment of the PF x alpha and MF x alpha. So here is the theorem by Fugri and Ganguly, is that there exists an absolute constant C such that PF x alpha is less x times exponential minus C square root of log x. This is true for all alpha. And similarly, for MF x alpha also, we have the same estimate. The striking part of the theorem is that, okay, you can check that, see immediately that, this one is much stronger than these two. However, as I mentioned earlier, that the first one is not uniform in alpha, while the result of Fugri and Ganguly tells that this equation 1 and 2 is valid for every alpha. And in fact, the absolute constant C that doesn't depend on alpha. Okay. So, well, it was the term of strong asymptotically orthogonality was first coined by Green and Tao. Yes, so that according to their declaration, this lambda Fn, the Fourier coefficient, is strongly asymptotically orthogonal with the sequence lambda n e of n alpha, and also for mu n e of n alpha, which follows from 1 and 2. And here, I must say that this exponential thing in both these cases are saying that these are gives much bigger setting than any power of log, and so for any log power saving, the term strong orthogonality here first coined by Green and Tao, and so in that sense, these bounds are even stronger. Stronger than this strong orthogonality. Okay, fine. Now let me say a few words about the idea of Fugri and Ganguly. So basically, they first use the rational approximation, and by means of that, so it is enough to consider alpha to be a rational up to an admissible error term. And suppose alpha is a rational and it is given by A over Q, where A and Q are coprime, and the rest of the proof depends on the size of Q, the denominator of alpha, denominator of the rational that approximates alpha. So if the size of the Q is large enough, then we'd say that alpha lies in minor arc, and if it is small, then we'd say that alpha lies in major arc. Here the term small or large seems a little vague, but here actually by small or large, I mean that in comparison with the length x, these are small or large. So in the major arc, so they use some analytic properties of modular forms and give some non-trivial estimate. And while in the minor arc, basically the arithmetic properties of the Fourier coefficients have been used. And two basic important tools are here in the minor arc. One is the Von's identity, which is available for both lambda n and mu n, And secondly, it is the estimation for the bilinear exponential sums. So, I mean, it is all, I mean, they also claimed that in their paper that if alpha is alpha can be approximated by a rational with some where the denominator is not too large or too small, in that case, we can have some improved estimate. In particular, for the golden ratio rho, they have proved that MFX rho is less x to the 59/60. All right, I'll come to that later also. Anyway, so our idea lies between the result of Hoogley and Ganguly and this one. So whether we can improve these two inequalities 1 and 2, and also if it's not possible for all alpha, at least if we are trying to find if for some certain alphas we can have a power saving estimate just like that. It might not be as strong as it is, but we need some specific values of alpha for which such power saving estimates are possible. Okay. Here comes the continued fractions, as it was mentioned by Hoogley and Ganguly also in their paper. Okay, so suppose this is, alphas, the continued fraction is given by this, and if we terminate this continued fraction at the nth place, then what we have is called the nth convergent of alpha. So naturally, as it terminates, it is a rational, and we call it, say, the numerator is hn alpha and the denominator is kn alpha. Okay, so we'll follow this notation throughout. So this hn and kn are given by some recursive relations, as you can see here. Yes, and next, so it follows from this recurrence relation that the denominators kn alpha for the convergence is strictly increasing. Well, so after that observation, here comes a theorem. By the theorem is actually due to Khinchin, but so the Khinchin theorem tells us that for the full Leibniz measure, almost all alpha, where alpha is irrational, we have this kn alpha to the 1 over n. This is convergent, and the value is 3.275 or something. So the Khinchin's theorem actually deals with the convergence of this sequence, and the limit is due to Levy, and it's known as Levy's constant. All right. Okay. Next, the relations between continued fraction and rational approximation. Okay. We'll use this notation, is that if, any irrational number alpha. So from now on, by alpha, we mean an irrational number. And this alpha is approximated by some rational A over Q, and we are considering only those approximations if this happens. Okay. So the size of the error term, error in the approximation is less 1 over the square of the denominator of the ratio. Next, so for irrational alphas, there exist infinitely many such approximations. So clearly, so for any given A, there exists some rational approximating alpha such that Q is bigger than alpha, bigger than A. Similarly, so just take another parameter B, and for that, by Dirichlet's theorem on Diophantine approximation, so we have similarly alpha can be approximated with a rational where the denominator of the rational is less than equals to B. So for any sufficiently large A, we can find a rational approximation with denominator bigger than A, and similarly for anything, any real number B, so we can have an approximation where the denominator is less than equals to. Now the question is, if two real numbers A and B are given, so can we find a rational approximation where the denominator of the rational lies in that interval AB? So this is a crucial question. However, so the answer is not always affirmative. By the way, so as we defined earlier, the convergence for alpha, nth convergent. So each convergent approximates alpha in the above sense. And not only that, I must say also that so this approximation is the best in the sense that the error in approximation is smaller. Okay. Fine. Now another notion of quadratic rationals. Before that, well, a continued fraction is called periodic if there exist some, two integers k and n naught, such that a n plus k is a n for all n greater than or equals to n naught. That means after certain stage, the sequence n is periodic. Now, what is quadratic rationals? These are basically irrational real roots of quadratic equations. So given a quadratic equation, ax squared plus bx plus c is equals to 0. So the coefficients a, b, c are integer here, and the discriminant is greater than 0. So that means the roots are real and not perfect square. So this means it is rational. Well, these are, so by quadratic rational number, we mean that. So Euler proved that if alpha admits an periodic continued fraction, then it must be a quadratic irrational. The converse is also true by the work of Lagrange. So the notion of periodic continued fraction and quadratic irrationals are exactly same. Well, so an example. So this example will appear many times in the talk. So this rho is the golden ratio, 1 plus square root of 5 over 2. So the continued fraction of rho is given by that. As you can see, this is periodic, and as a consequence of that, the convergent for rho are given by fk plus 1 over fk, where fk's are nothing but the Fibonacci sequence. I mean, fk is the kth member of the Fibonacci sequence. All right. Okay. Next. So what is our result here? So f is a holomorphic class form, as we have defined earlier. So, and suppose that there exists a pair of co-prime integers aq such that alpha can be approximated by the rational a over q. In that case, we have such an upper bound for pfx alpha and mfx alpha. Well, just look at the estimate here. So the second term here, you can see that this is non-trivial only if q is large enough in terms of x. On the other hand, the third term tells us that q cannot be very large. I mean, in fact, q cannot be bigger than x. Okay. So to get an power saving estimates for pfx alpha and mfx alpha, we require q to lie in a certain interval. Okay. What is that? Yes. So another one. If q lies between that interval for every sufficiently large x, so in that case, we have a power saving estimate is x to the 15 over 16. Well, so that, I mean, that exactly follows from the first theorem. Is that it states that, again, I'm repeating it, alpha be such that for, I'm sorry for this typo, alpha be such that for any sufficiently large x, there exist co-prime integers aq with such an approximation where q lies between x to the 1/4 and 3/4. In that case, pfx alpha and mfx alpha can be bounded by x to the 15 or 16 times some power of log. Okay. So now the question is that whatever we have done is for these Fourier coefficients or Hecke eigenvalues, whatever you can say. Now, is there any generalization for certain choice of multiplicative arithmetic function? Okay, let us see a more general result. Well, the general theorem states that, say, if g is an arithmetic function which satisfies a multiplicative relation of that kind, gm times gn is given by sum over d divides the gcd of mn, a of d times g of mn over d square where AD is less tau d whole to the power k. Well, I must mention here that this is AD is less tau d whole to the power k for some integer k. Well, next is that sum over, the second moment of this Gn is less x to the x times log x to the a for some a for some real number a. Well, you can see that the first one is the replacement for the Hecke multiplicativity. In fact, so this works not only for Hecke multiplicativity thing, for completely multiplicative function, this also is also true. For a1 is equals to 1 and 0 else. So in that case, J is completely multiplicative. And the second condition is that this is generalization for the Delling's bound. A more relaxed condition. So up to these two relaxation, we have that, well, we have one more condition is that the unrestricted exponential sum n up to x Gn times E of n alpha is x to the theta for some theta lying in 0 and n. So we require the power saving for this Gn also. Well, and so if G satisfies these three conditions, then we have that for n up to x Gn lambda n E of n alpha, the sum corresponding to Pf alpha and the sum corresponding to Mf alpha is that for just lambda f replaced by G. So in that case, it is also, power saving estimate is possible where this eta depends on theta. In fact, eta is bigger. So this is the general result. And I'll finish with some remarks on these theorems. What is that? First one, here 5 means the final power saving estimates. That 5 holds for all quadratic rationals. Okay? That means all real irrational roots for quadratic equations. Next, so as you can see is that the golden ratio rho is a quadratic rational, follows, it admits a continued periodic continued fraction, and for that we have the power saving estimate x to the 15 over 16, which improves the earlier estimate by Fougli and Ganguly, which states that in a rho is less 15 x to the 59 over 16. So our result gives significant improvement in that case for quadratic irrationals. Next remark is that if alpha satisfies 4, here 4 is the equation, the Khinchin's theorem, where the alpha satisfies 4 means that Kn alpha, the denominator of the convergence, Kn alpha to the power 1 by n, that converges to the Lewis constant. So in that case, we have the power saving estimate for alpha. For Pfx alpha and Mfx alpha. Next. So in the general theorem, so So it gives a way. So our result can be viewed in a way that if the unrestricted exponential sum is Gx alpha, for this sum, the estimations are known, the same can be obtained for the restricted exponential sum over primes and the twisted exponential sum by Mobius functions. So once you know something about the unrestricted sum, then you can estimate non-trivially the restricted sum and the twisted sum, the type 1 sum and the type 2 sum. So of course, G needs to be some nice arithmetical function. So here nice means the conditions of the previous result. Well, and finally, more thing is that, so as you can see that the Delling's bound can be replaced by the second moment. So our result can be extended not only for holomorphic class forms, but for Heike-Mass class forms, this also holds true. And however, the GLT analog of this problem is beyond the reach of this method. So, well, the GLT analog for the results of Fugri and Ganguly, it was studied extensively. First, it was by Jiang and Lu, is that they are proved for the restricted type 1 exponential sum, and the type 2 sum for the GLT case was also been done by the speaker. And recently, Jiang and Lu and Hao also, they improved the type 2 sum for the GLT case also. And by GLT analog, we mean that this is, the coefficients, instead of lambda fn, you can insert the coefficient of Bodmer-Jacobi L function. Well, so the reason behind this is the fact that the GLT coefficients are not Haken multiplicative, even not in the sense of the general theorem. So this is the end of today's talk. Yes, thank you.
Thank you, Dr. Acharya, for a nice talk. Are there any questions for him?
I have a question.
Sure, Stephen.
Yeah. So you mentioned this result by Khinchin, which is quite amazing. I didn't know about that. So that for almost all alpha, we have that the denominator to the 1 divided by n tends to this constant, Levy constant. Do you know what goes into the proof? How this is proved? Yeah, besides that.
Proof of Khinchin's theorem, or?
Yeah. No. Of, I mean, whose theorem is it? Khinchin.
This is Khinchin's theorem.
Okay. And how?
And
do you know
in that
how
theorem, yes, proceed.
Yeah, I just wanted to know what goes into the proof. I mean, how does this constant come up in particular?
Well, no, I'm not sure about the proof. I've just, seen the result here. In fact, this one is, was not the part of the Khinchin's theorem. It was proved later by Levy. The convergence is only due to Khinchi, and it's remarkable.
Yeah, it's very remarkable. Yeah, good, I will look into that. I am interested to see that. Thank you.
Sir, you have to unmute.
Oh, I'm sorry.
Yeah.
Yeah. So any further questions? Yeah, if not, let's thank Dr. Acharya again.
Thank you.
Okay, over to you, Pallab, or the local organizers.
So Sajjad, could you say?
Yeah. So it is a great pleasure for me to say a few words at the end of this conference. On behalf of these organizers, first I would like to thank all the invited speakers for their nice talks and the chairs for conducting all the sessions smoothly. I would also like to thank to our university IT department for creating the conference web page and conducting all the Zoom sessions without any interruption. Here especially I would like to mention Mr. Venugopal, Mr. Nitin, and Ms. Ananya for their supports in this regard. I would like to thank our department and colleagues for supporting to organize this event and ensuring it ran so smoothly. Especially I thank our colleague Manish for proposing this conference. I also note that we would like to have many more similar events at our university in the near future. As Professor Kannan mentioned in his opening remarks that our university is very young, so I earnestly request all the speakers, colleagues and participants for your supports and suggestions. The way you have shown us now, we want to make our department as a mathematically active department. So your suggestion and feedback will always be appreciated. Finally, last but not the least, I express my sincere gratitude to all the participants for making this conference a successful one, although the last 2 days were holidays. So we thank you once again for your active participation and wish you and your loved ones health and safety in this ongoing difficult time. In the near future, see you all. One final announcement, the slides and videos of the talks will be uploaded on the conference web page. So I request all the speakers for sending the slides of your talks to my colleague Pallav Gandhi. As to participation certificate, to all the participants, if you need your participation certificate, please write to my colleague Pallav Gandhi. Have a nice evening. Thank you all.
Let us clap finally for everyone.
So,